Generative artificial intelligence requires massive physical infrastructure. Training a modern large language model takes thousands of interconnected servers operating around the clock, drawing enough electricity to power a small city. That exact same computational power drives our national security apparatus. Advanced military hardware, like the targeting and avionics systems inside an F-35 fighter jet, relies entirely on the rapid processing of complex data streams. Both of these apex technologies run on microchips. Those chips are carved from silicon, and because silicon makes up over a quarter of the Earth's crust, there is a pervasive assumption that the digital economy is built on an endless supply of common beach sand. If you actually tried to melt down typical beach sand to build an AI processor, the resulting material would be riddled with metallic impurities. The moment you applied power to the device, it would short-circuit and instantly self-destruct. The modern digital age is restricted by a standard of atomic perfection that practically does not exist in nature. We are entirely constrained by the need for materials that are pure down to the parts per trillion level. To build a functioning silicon wafer, atoms must lock into a diamond cubic lattice. This is a highly specific, perfectly repeating geometric structure, where each silicon atom binds identically to 4 neighbors. Across this vast two-dimensional plane, a single misplaced metallic atom, like iron or copper, acts as a roadblock. If an electron hits that contaminant, it derails, causing logic errors that corrupt trillions of operations per second. This physical vulnerability scales directly with the size of the chip. An advanced AI accelerator can reach 814 square millimeters, which is massive compared to the processor inside a smartphone. As the active area expands, the mathematical probability of a fatal atomic defect intersecting with critical circuitry increases exponentially. Engineering this flawless atomic structure is the most unforgiving manufacturing challenge on Earth. Before a chip can be printed, the raw silicon must survive a violently extreme thermal environment without picking up a single stray atom. Over 90% of the world's monocrystalline silicon is grown using the Czochralski process. The Czochralski process is a demanding metallurgical technique that extracts a single continuous crystal from a bath of liquid silicon. To execute this crystal growth, raw polysilicon must be melted and held at 1414 degrees Celsius. The liquid must maintain that blistering temperature for hundreds of hours, completely without interruption. This creates a severe containment paradox. At 1414 degrees, liquid silicon is a highly aggressive solvent. Almost every known material on Earth will either melt, structurally deform, or chemically react with the liquid, ruining the batch. The only physically viable solution is a specialized containment vessel, a crucible, made entirely of ultra-high purity fused quartz glass. Because the highly reactive liquid silicon slowly physically erodes those quartz walls over time, the crucible itself becomes the primary source of potential atomic contamination. If the crucible contains even parts per billion of impurities, those elements are released directly into the melt. As the walls dissolve, microscopic particles of metals like iron leaching into the liquid silicon. When an iron atom gets locked into the final silicon crystal, it creates a deep-level trap. The iron atom swallows signal-carrying electrons, stopping the electrical pulse and causing logic operations to fail completely. Trace alkali metals behave differently. Sodium ions act as wandering ghosts, drifting straight into the transistor's gate oxide. Their presence shifts the voltage thresholds, causing the transistor to misfire at the wrong time, a fatal error for neural networks that rely on exact synchronization. To prevent these microscopic saboteurs from destroying the chips, the quartz used to build the crucible must be 99.999% pure. That is a standard of geological perfection that nature rarely produces. This impossible standard of quartz practically exists in only one place on the planet, the Alaskite pegmatite deposits of Spruce Pine, North Carolina. Roughly 380 million years ago, the massive tectonic collision that formed the supercontinent Pangaea forced specialized, mineral-rich magma 20 to 30 kilometers underground. Typically, underground water introduces metallic impurities into cooling rock, but this specific magma cooled under immense pressure in an anhydrous, or completely water-free, environment. As a result, the quartz crystallized flawlessly, rejecting trace metals. This waterless cooling process was a geological freak accident. Millions of years before humans existed, the Earth accidentally solved the exact chemical tolerances required for a 21st century quantum physics problem. Because this geological lottery is practically irreplicable, an estimated 70 to 90% of all the ultra-high purity quartz used in global computing comes from this single small district. This diagram shows how that extreme geographic concentration creates a severe single point of failure. The raw material from the Spruce Pine mine flows through crucible manufacturing and wafer fabrication, directly feeding the trusted foundries that build U.S. military systems. The physical fragility of this choke point was exposed in late 2024. Catastrophic flooding from Hurricane Helene washed out roads, severed power grids, and completely halted mineral output in the region. This chart illustrates how the U.S. government evaluates supply chain risks. Because spruce pine quartz is mined entirely within the United States, federal algorithms mistakenly classify it as fully secure, placing it squarely in a policy blind spot and excluding it from the official critical minerals list. Federal models heavily prioritize import reliance. By conflating domestic production with absolute supply security, these methodologies completely ignore the systemic risk of having a hyper-concentrated geographic point of failure sitting right in our own backyard. We have built the most advanced digital architecture in human history. The artificial intelligence revolution, the global economy, and modern military deterrence all balance on the terrifyingly fragile foundation of a single Appalachian Valley.